Hello, I am Dr. Sigar Kanti, Associate Professor of Mathematics, Government First Grade College, KR from Bangalore. In this video, I am going to discuss some more basic concepts of graph theory. Okay, one result is there. I'll take this as a theorem. The number of odd vertices means odd degree vertices. Odd vertices, we write odd degree. Okay, vertices is even. Okay, so that is suppose there are odd vertices, then the number of odd vertices, odd degree vertices is always even. This we have to prove. So to prove this, we have sum of the degree is equal to 2 cube. Okay, this already we have proved. So that is here sum of the degrees is equal to 2 cube, means it's some even number. Okay, now here let the vertex set V be divided into say two subsets say V1 and V2, where degree of each vertex in V1 is odd and degree of each vertex in V2 is even. So that is, we are dividing the vertex set into two subsets, V1 and V2. That is, V1 is the set of vertices of odd degree and V2 is the set of vertices of even degree. Then sum of the degrees of V1 plus sum of the degrees of V2 must be equal to sum of the degrees of the graph. So that is here sum of degrees of V1 plus sum of degrees of V2. This gives the sum of the degrees of the vertices, and we know that this is nothing but even. Okay, but here I will consider, if possible, I have to prove that the number of vertices in V1 is even. That we have to prove. Okay, that we have to prove that the number of odd degree vertices is even. So here I have taken V1 is the set of vertices consisting of odd degree vertices. I have to prove that the number of vertices in V1 consisting of even number of vertices. Now I will consider negation. If possible, V1 consisting of odd number of vertices. If possible, V1 consists of odd number of vertices. Okay. So here V1 constituted, how many vertices are here in V1? Odd number of vertices. Okay. And what is the degree of each vertex? It is equal to odd. So that is here. What is the value of the sum of the degrees of V1? It is odd times odd. Odd times odd means we get this is equal to odd. Okay. So that is, I'll go to the next page. Sum of the degrees of V1 is equal to, I am getting odd plus see here V2 is the set of vertices consisting of even number of vertices. And whatever may be the number of vertices in V2. But if I get the sum here, because degree of each vertex is even, therefore sum of even degree vertices is again even. So that is here we get this value equal to even. So this is our even. What is the right hand side? It is equal to even. So what I am getting here is odd equal to even minus even. That is here. This gives, sorry, odd plus even is equal to even. So this is the sum of the vertices of V1, and this is sum of the vertices of V2. That is, I have taken V1 consisting of odd number of vertices, and degree of each vertex is odd. So that is odd times odd, definitely this value equal to odd. And the V2 is the set consisting of even degree vertices, and whatever may be the number of vertices in V2, but their sum always it is equal to even. And right side, this is the even quantity. So that is here odd equal to even minus, taking this even to the right hand side, even minus even. So that is here odd is equal to even minus even, again I will get a even number. So what I am getting here is odd equal to even. So is a contradiction. This is a contradiction. This is a contradiction. Why we are getting this contradiction? Because of this. That is, if possible, V1 consisting of odd number of vertices is wrong. Therefore, V1 consisting of even number of vertices. So that is here. This implies V1 consists of even number of vertices. Okay, even number of vertices. That is, this shows the number of odd vertices in any graph is equal to even. Okay, and we can verify this with some examples. So here I will take an example. This is an example. Here, this is odd. Okay, this vertex is even. This vertex is of degree even because it is equal to 2. See here, this is a vertex of odd degree because its degree is equal to 1, 2, 3. And this is also vertex of odd degree. So here, how many odd number of vertices are there? The 2 odd number of vertices equal to 2. This is even. We can consider another example. This is the example. Okay, this is the example. See how many odd number of vertices are there. If you go to this vertex, this is 1, 2, 3, 4 even. This is 1, 2, 3, this is odd. And this is odd, 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 odd. So how many odd number of vertices are here? 1, 2, 3, 4, 5, 6. So that is here. Number of odd vertices is equal to 6. This is equal to a even number. Okay. Next I will go for some more basic definitions. Finite finite graph. Finite graph. So that is, we say that a graph G equal to VE is finite if both vertex set and a set are finite. So that is here a graph G equal to V comma E is said to be finite if both V and E are finite. Okay, that is finite number of vertices and finite number of edges. Then we say that it is a finite graph. What is infinite? If at least one of this V or E is infinite, then we say that it is a infinite graph. So that is here infinite graph. Infinite graph. A graph G equal to VE is said to be infinite if at least one of V a E is infinite, then you say that it is a infinite graph. That here, if V is infinite, then you say that G is infinite. If E is infinite, then also we say that G is infinite. Or both are infinite, then you say that again this G is infinite. If both are finite set, then you say that the graph G is finite. Otherwise, we say that it is a infinite graph. Okay. Next, we define multiple multiple edges. Multiple edges. So that is here we while defining graph we have defined that uh, the elements of E are the pairs of V. So that every element is element of E is said to join two members of V. Okay. Now if we allow more than one edge between the same two vertices, then you say that it is a multiple graph. So that is here we define like this: if more than more than one edge is allowed between between two vertices say U and V, then the graph is called multigraph. Or we say that these edges are multiple edges, okay, called multigraph, and and the edges are called multiple edges are called multiple edges. So that is if U and V are any two vertices of a graph G, if more than one edge is allowed between U and V, then we say that those edges are known as multiple edges, and the graph is known as multigraph. For example, we write G. So this is a multigraph because here we have these are two vertices here. In between these two vertices, we have two edges. So this is known as multi-graph, and these edges are known as multiple edges. So that is a graph having multiple edges is known as a multi-graph. Okay, many examples. We can take only two vertices here. We can take many edges here. Okay. So this is a graph with two vertices, and we have multiple edges are there. Therefore, we say that this graph is a multi-graph. Or we can add some more edges here, some more edges, some more vertices. Okay. So this is a multi-graph, right? Then we define loops. Loops. So that is the loops means if there is an edge joining U onto itself, then we say that it is a loop. That is the edge joining U and U to itself is called a loop. Okay, is called a loop. For example, I'll consider a graph. Okay, so this is a loop. Okay, this is a loop. See, there is a loop here. This is an edge joining this vertex onto itself. Therefore, we say that this is a loop. There may be many loops here. Okay. So, one more loop. And here is one loop. Here is one more loop. Okay. So, these are known as the loops. The loops are nothing but the edges joining a vertex to itself. It is known as loop. And suppose there is a graph consisting of both multiple edges and the loops, then you call that graph as a pseudograph. That is, pseudograph is pseudograph. So if multiple edges and loops are allowed in a graph G, in a graph G, then G is called pseudograph. Pseudograph. Okay. So if both multiple edges and the loops are allowed, then you say that it is a pseudograph. Let me write an example for the pseudograph. G. See, this is the pseudograph. Sorry. Multiple edges I am considering, and we take one more edge, vertex here. This is an edge, this is an edge, and I will take a loop here. Okay, so this is the graph consisting of both multiple edges and the loops. Therefore, we say that this is a pseudo graph. Okay, then we go for some more definitions in graph theory. First, I will go for walk. Walk. Walk is nothing but it is similar to our walking in the morning. What we do here is we put a step here, then this is the second step, third step, fourth step, fifth step, sixth one, seventh one, eighth, ninth, 10, 11, 12, 13, 14, like this. So this is a walk here. So that is I have started somewhere here, then I am walking. Okay, just I am walking. And here walking means what I do here is the first step I will denote this by a point. Okay, a point, a vertex, and second step again a point, and in between first step and the second step I will draw a line here. And here the vertices may be repeated. Vertices may be repeated. Edges may also be repeated. That is, suppose if I am here, again I can come back with the same uh, edge here. Again I am coming to the same vertex here. Again I will go to this vertex here. Again I will go to somewhere here. Again I will come to this vertex. Again I will come to this vertex. So that means here I am repeating the vertices and the edges. So that, but here it I have started with a vertex. After vertex, an edge is there. Again a vertex, again an edge, again a vertex, edge, vertex, and I have ended with some point here. So I have started with a point and ended with a point, and in between 2 points there is an edge here. So that means here walk is nothing but alternating sequence of vertices and edges, starting with a vertex, ending with a vertex, and every edge appear in between two vertices must be incident with immediately preceded and followed by it. So that is, if I write this vertex, then I have to write this edge, or I have to write this edge. I can't write this edge here because here this is not an edge between this and this. Okay, vertex, then you have to take the edge, and next vertex, edge, vertex, edge, vertex, edge. So here we define a walk is an alternating sequence of vertices and vertices and edges, starting with starting with a vertex, and ending with a vertex. But this is not sufficient for the definition. I have to tell about the edge here, and every edge every edge in the sequence, every edge in the sequence is incident with, is incident with the vertices immediately preceded and followed by it. Okay, so that is, walk is nothing but an alternating sequence of the vertices and edges, starting with a vertex, ending with a vertex, and every edge in that sequence must be incident with the vertices immediately preceded and followed by it. Let me go for an example to understand this concept. See, here I will write G, 1, 2, 3, 4, 5. Okay. So if I write W1, 1 comma, I'll write first 1, 1, 2, 2, 2, 4, 2, 4, comma, 4, 4, 5, and final 5. Okay. We are writing this. See here, this is a vertex, edge, vertex, edge, vertex, edge, vertex. That is, this is the alternating sequence of vertices and the edges, starting with a vertex and ending with a vertex. And one more condition is there. Every edge in that sequence must be incident with the vertices immediately preceded and followed by it. See here, this is the edge. 1, 2 is the edge. Is this edge incident with 1 and 2? Yes. Next. This is an edge 2, 4. Is this edge incident with 2 and 4? Yes. And 4, 5. Is this edge incident with 4 and 5? Yes. Okay. Therefore, this is a walk. And we write simply this as like this 1, 2, 4, 5. Okay. This is a walk. Instead of writing the edges here, I will write just the what I said. Understood that from this to this there is an edge. From this to this there is an edge. From this to this there is an edge. So here W1 is a walk. I will go for another example here. 1, 2, 3, 4, 5, 4, 2, 1, 2, 3. Is this a walk? Yes, definitely. See here. 1, 2. 1, 2, then 3, okay, 3, 4, 5, again 4, again 2, then 1, 1 to 2, 2 to 3. Yes, this is a walk here. And if I write one more here, 1, 3, 4, 5. Okay. Is this a walk? No. Because 1, 2, 3. If I from 1 to 3, there is no edge here. Okay. So therefore, this is not a walk. This is not a walk. Similarly, 2, 3, 5. Is this a walk? Let me check. 2, 3, okay. 3 to 5, there is no edge here. So therefore, this is also not a walk. Okay. So this is about the walk. Here, see this walk we have repeated the vertices and we have repeated the edges also. Now if you put some conditions on this repetitions, then you get some different definitions here. So here edges are also repeated, vertices are also repeated, may be repeated in a walk. There is no condition, just it is a alternating sequence of the vertices and edges starting with a vertex, ending with a vertex, and every edge in that sequence must be incident with the vertices immediately preceded and followed by it. This is the definition of a walk. Now, if I put some condition here, that is, suppose if I put condition in a walk, edges are not repeated, then we call that walk as a trail. So, we define trail as, so we define one more thing here, trail, T-R-A-I-L, trail. So, if edges are not repeated in a walk, in a walk, then the walk is, then the walk is defined as, is defined as a trail. Okay, defined as a trail. Let me go for an example. I take G, 1, 2, 3, 4, 5, 6, okay, 7. So if I write T1, I write 1, 2, 4, 1, 2, 1, 1, 2, 4, 5, 6, 4, 7. Okay. Is this a trail? Yes, I think. See here, 1, 2, 2 to 4, 4 to 5, 5 to 6, 6 to 4, 4 to 7. So that is no edge is repeated here. And this is a walk. One vertex is repeated. That is the vertex repeated for 2 times here. But vertex may be repeated in a trail. Edges are not repeated. Therefore, this is a trail. I'll consider another example. 1, 2, 3, 2, 3, 4. Is this a trail? See, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, again 2. So that means I am repeating this edge here. 2, 3 is repeated twice. So therefore, if it is repeated, then it is not a trail. But definitely this is a walk here. 1, 2, 1, 2, 3, 2, again 3, okay, again 3 and 4. This is definitely a walk, but it is not a trail. Not a trail. I go to another example. T3, 5, 5, 4, 3, 5, 4, 5, 4, 3, 2, 4, 7. Is this a trail? I think yes. 5, 4, 3, 2, 4, 7. Yeah, no edge is repeated here. One vertex is repeated. Okay, no problem. 4 is repeated 2 times. So that is, this is a walk and there are no repetitions of edges. Therefore, this is a trail. Okay. And if you put one more condition, that is the edges are not repeated, then we call it as a path. And consequently, vertices are not repeated, then we say that it is a path. Edges are not repeated, it is a trail. Vertices are not repeated, then we call it as a path. And if I say that vertices are not repeated, consequently, edges are also not repeated. That is no need to say that vertices and edges are not repeated. Just if I say that vertices are not repeated, then definitely edges will not be repeated. So that is, we call that as a path. So we define path, path. That is here, a walk is a path. A walk is a path if no vertex is repeated. No vertex is repeated. I will consider an example. Okay, this is an example. Now here, I write 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose if I write 1, 2, 3, 4. Is this a path? I think yes, it is a path. See, 1, 2, 3, 4. Vertices are not repeated here, and this is a walk. Okay, so this is a path. And I write 1, 2, 5, 6, 7. Is this a path? Yes, this is a path because here 1, 2, 5, 6, 7. This is a walk. No vertex is repeated. Therefore, this is a path. Next, I will go for another example. 1, 1, 2, 1, 2, 5, 9, 1, 2, 5, 9, 6, 5, 3. Is this a path? I don't think. Because here, see, 1, 2, 5, 9, 6, 5. See, I have already taken this 5. I am repeating this 5 and I am going to 3 here. Okay, so therefore here, this is not a path. Is this a trail? Yes, because no edge is repeated. 1, 2, 5, 9, 6, 5, 3. No edge is repeated. Therefore, not a path, but it is a trail. But it is a trail. It is not a path, but it is a trail. I will consider another example. Say 1, 2, 3, 5, 9, 6, 5, 5, 3, 4. Is this a path? No, because see here in this sequence, 3 coming twice here and 5 also coming twice here. That means here vertices are repeated, therefore this is not a path. Is this a trail? Let me check. 1, 2, 3, 5, 9, 6, 5, 3. See, the 3, 5 I have taken. So that is here. 3, 5 already I have used here. And again I am getting this 5, 3. That means here the edge 3, 5 is repeated twice. Therefore, this is not a trail. So this is not a path and it is not a trail, but it is a walk. It is just a walk. Now, if I consider another example, 1, 5, 6, 7. Is this a path? No. Because here 1 is here, 5 is here. There is no edge between 1 and 5. Okay. So that is these two must be adjacent to each other. There is no edge between 1 and 5. Therefore, this is not a walk. If this is not a walk, then this is not a trail, not a path. Okay. So this is not a walk. And here a path is there. Definitely it is a trail. Okay. If trail is there, then it is nothing but walk. So that is here. Every path is a trail and every trail is a walk. But the converse is not true. Every walk need not be a trail. Every trail need not be a path. Okay, these are some basic definitions in graph theory. Okay, thank you. I will stop here.